You have likely encountered AI slop that sounds confident but is fundamentally wrong. It feels like a human wrote it, yet something about the logic falls apart in mid-sentence. Most people blame the model's intelligence or assume they are dealing with bad training data. They do not realize the root cause lies in the physics of their graphics card. When an LLM runs on consumer hardware with limited VRAM, typically between 12 and 24 gigabytes, it hits a hard memory wall during inference. This physical constraint forces aggressive truncation and early stopping, creating what we call hallucinated confidence. The text sounds authoritative because the model is guessing rapidly to fill space, not because it understands the facts. To understand this phenomenon, we must first look at how these systems actually operate under pressure. Modern large language models do not just generate words, they rely on a massive amount of temporary data called key-value caches stored directly in GPU memory. Think of this cache as the model's short-term memory while it is reading and writing your prompt. When you ask for a long document or a complex analysis, that cache grows rapidly. If the demand exceeds the physical capacity of your video card, the system faces an impossible choice. Slow down drastically to use slower host RAM, or cut off parts of your request entirely. This creates a critical bottleneck known as memory wall saturation. Research from IBM and the Barcelona Supercomputing Center confirms that large batch LLM inference hits this DRAM bandwidth limit long before it becomes compute-bound. The GPU cannot process data fast enough if it has to constantly swap information in and out of slower system memory. To avoid this, systems prioritize stability over utilizing full VRAM capacity. In practice, when the cache exceeds available space, the engine must preempt requests or evict critical context data immediately. This leads to a scenario where the model literally runs out of room to think about what it just said before continuing. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The cost of trying to bypass this limit is staggering. If an inference system attempts to overcome VRAM limits by spilling data into host memory, performance can degrade up to 78 times slower due to poor data locality. This means a task that should take seconds could stretch out for minutes or hours. Because waiting that long destroys the user experience and breaks real-time applications, engineers have no choice but to default to truncation modes. The system chooses to cut the context window short rather than suffer a 78-fold penalty in speed. This hardware-driven decision is why you see such distinct patterns in low-quality AI output. When the model cannot access its full training context due to these memory limits, it begins to hallucinate with high confidence because it has no data to ground its answers in reality. It starts generating text based on probability rather than retrieved facts. The microarchitecture of GPUs relies on coalescing memory requests for speed, but when these mechanisms are stressed by large contexts, the system prioritizes throughput over coherence. This results in repetitive phrasing or disjointed logic that defines slop not as a software bug, but as an inevitable side effect of running massive models on limited consumer hardware. You can spot this behavior in the wild if you know what to look for. Look for text that starts with strong, specific details and suddenly drifts into generalities or abrupt endings. This is often where the truncation point was hit during generation. The model ran out of space to maintain its train of thought, so it defaulted to a safe but when the system cannot recall previous context because it had to evict that data from VRAM to make room for new tokens, it may repeat arguments or restate points as if seeing them for the first time. These are not signs of an intelligent model making a mistake. They are artifacts of forced memory management. The hardware is simply doing what it must do to keep running within its physical constraints. Understanding this shifts your perspective from asking whether text was generated by AI, which relies on unreliable black box detectors, to diagnosing why the output feels off based on engineering reality. You can now predict quality issues before generation even starts by looking at the context window size against available VRAM. This insight changes how you should approach local deployment and RAG systems in your own work. A consumer-grade GPU with 12 gigabytes of memory might struggle to produce coherent long-form content compared to an enterprise card with significantly more capacity, not because the model is weaker, but because it has less room for its working set. As a practitioner, you now know that hardware specifications matter just as much as algorithmic choices when it comes to output quality. The next time you see Slop, do not blame the AI's intent or training data. Look at the memory wall and understand that the model was simply forced to guess because there was no space left for truth. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.